Okay, some update to our syllabus. So now we have an official TA, and and his name is Xin Yao. So this is his name. So Xin, can you come up? Yeah, just yeah, go up. Yeah, and also Leo, come on. So basically, Xin is my PhD student, and so he will be your lab TA. Okay, and so because we have so many labs here, and so now we have 3 lab sessions, and so my another student, his name is Leo Wang. So yeah, he's not official TA for this class, but he may help Xin for the labs. So sometimes you may see him instead of Xin. So if you see him, don't be surprised. Okay, so yeah, I think just want to introduce him to you. Yeah, you can say a word or two.
Hi everyone, my name is Xin Yao. I'm happy to help you with the lab sessions. So if you have any questions, feel free to reach me out. Shoot for email or just meet me in the office. Thank you guys.
Yeah, do you want to say anything?
Sure. Yeah. I'm new to this class. I'm learning with you guys, so we can keep on discussing on that. Have questions, we solve that together. Yeah. Hopefully, we can have a semester for this course and have you guys be successful on the course.
Yeah, he's not really new to the concept, right? So yeah, he learned this class before. He just maybe some labs is he have not done that before. He need to do that before. Okay. Okay. Yeah, I think that'll be it. So yeah, you can do whatever you want. Okay, great. So yeah, just some logistics of this class. So first, yeah, as I said before, so for this class we have 2 online tools that we can use. One is a course website. So if you go to my homepage and click teaching, and then you can see this class here, right? If you click it, then you can see the current content here. So I didn't put the labs here yet, but I'll update the page as soon as possible. Now we have if you click syllabus, and then you can download the syllabus, okay, and so on. And so we have the lecture video of last time here. So if you want, you can watch the video on YouTube. Okay, and similarly for our for the Canvas, so basically I mainly use page. Okay, so you can see now we have lots of information here. So those are all the sessions. If you click one of them, you can see, for example, if you click the lecture slides, then you can see our first slides of the first lecture here. Okay, and just go to the pages, and then you can find whatever you want. And also, if you want a particular file, you can go to the files. So we have folders here for you to download and so on. Okay? Yeah, any questions? All right. Okay, so maybe since I think most of you are very new to GNU Radio, which is the main tool that we use for our lab. So for the I put the lab 0 here already, which will be due on January 24th. So basically, I don't have before. Normally, what I do is that if your lab session is on Tuesday, then your lab will be due on Tuesday. But since for this class, you don't really need to go to the lab if you know how to do that. Follow the instructions. Then I will put just a single date there for everyone. Okay. So basically, normally that will be the end of the week. Okay. So you can just follow all the steps here to do all the installation and take a look. Okay. And so on the pages, I have many many item here to help you to install the GNU Radio. And so if you're a Mac user, just follow the steps here one by one. Okay, so if you have any problem, just let me or the TA know about it. Okay, yeah, I think one problem usually I see when I install this is that sometimes some folder they want does not exist there. So you may just need to create a folder manually. Sometimes, not all the time. Depends on what kind of system that you are using. Okay, and so basically after all installation, so every time, oh, by the way, so it's suggested that you need to install the Anaconda, so this first, and then install GNU Radio under that, okay? Oh, by the way, so did you look at Lab 0 already? So who did that, or who installed GNU Radio already? Okay, is everything okay? Smooth? Okay, great.
I just used Radio before.
Oh, then, okay, great. And after that, so every time, so in the command window, so what you do is that you need to run conda activate gr. So gr is for GNU Radio. You just use gr. And then after that, you just use GNU companion. So this command to launch it. And then you can see the GNU Radio, right? So this is basically, I think that is probably a lab. What happened? Yeah, sometimes this kind of thing can happen. Yeah, let's see. Yeah, I think this is probably a Lab 0. Yeah, you can get something here, right? If you run that, you can see. So we have a complex signal, right? Signal 1, signal 2 are real and complex component. And then here's the frequency domain signal, right? So this, I think, is probably the result of your Lab 0 and something like that, okay? So just let me know if you have any question or comment on this, right? Any difficulty? Okay, I think that's what I want to cover before. Any question, comments? Okay, if no, yeah, let's get this disconnected. Yeah, I will try to use that. Hopefully it works. Okay, so as I told you before, so normally I don't use a lot of slides. So yeah, I think it's pretty efficient, but sometimes you cannot follow. Yeah, even for me, I don't feel extremely comfortable to use slides to cover everything, right? So normally I use lecture notes. I will just write on the board. Okay, so if there's so many tedious content, then I will probably use a little bit slides. Mainly I use slides for review. Okay, so I have slides for each class, but use that for review. Okay, so yeah, let's get started. So basically, this is our so today is our lecture number 2. Okay, so in the last lecture, so what we cover is the syllabus, the big picture, and also the history of telecommunications. Okay, so hopefully you enjoy something like that. And today we're going to something that is technical. So basically, we're going to introduce you, the concept of, the most basic signals that we're going to use in this class, and also some, background information about channel. Okay. So here's our agenda for today. First of all, we want to talk about the wavelengths. Of a signal. Okay, and then we're going to cover the effects of surfaces on propagation. Okay, so by the way, if you cannot see my writing, just stop me, right? I will explain, okay? So my handwriting sometimes can be confusing, but just, don't be shy. Okay, and after that, so basically this is to talk about, so in the last class, we emphasized that in our class, we mainly cover the RF signal, okay, the wireless signal, okay? And we don't cover other type of signal. So then it's basically transmit over the air, okay? And so for the second point, this is to talk about, what happened when the signal hit some surface, like this table or like this chair, right? What will happen, okay? So will this absorb that or reflect it and so on, okay? And after that, so we're going to talk about antennas. And how the signal will propagate using antennas. Okay, and then number 4. So we're going to talk about some basics using the decibel notation. Okay, so who used decibel notation before, dB? Okay, almost all of you, okay? So yeah, you may be very familiar with the concept. Let me just test you a little bit. So does dB have a unit? Who thinks it's yes? Can I say a power is 20 dB? Can I? Who thinks yes? Who thinks no? Excellent, great. Yeah, the answer is right. There's no unit. Okay, great. So basically, maybe I'll just quickly review, go through that, and then we're going to cover communication loss. Okay, because signal, when we transmit signal over the air, there will be some loss, right? How can we characterize it? Okay, so those are basically our agenda. Maybe we cannot cover all of them. So if we cannot cover all of them, then we'll just continue in our next class. Oh, by the way, I forgot to mention one thing. So we don't have class on Friday. I have to travel. Okay, so what I will do is that I will record it and then upload. Okay, so basically it means that if we cannot cover all of them today, so I don't have a time limit for the next lecture, right? I can record as long as I want. Then you can watch it online. Okay, so I have to leave right after the class, and then I'll record it on Monday. So I'll try to finish everything as soon as possible. So probably it's better for you to watch it on, for example, Monday night or Tuesday, and then we'll have another class on Wednesday. Okay, so all the concepts are not very hard. It's just definitions and so on. It should not be a very big deal. Okay. So I will send an email to remind you. Yes.
There's the case where we have the 2-hour block for the lab section on Friday. Should we not go to the lab section?
There's a 2-hour. What's that? There's a block on Friday.
On my schedule, I have a 2-hour block.
Oh, so you have a conflict on that, or you have a conflict on that, or?
No, I'm just wondering if we should show up to that tomorrow.
Oh no, the lab will start next week, not this week. Yeah. So basically, yeah, because the lab 0 will be due on I think next Friday. So if I remember correctly, so yeah, normally lab 0 will just take you maybe at the most 1 hour to finish. So it's a very, very basic lab. And also for the lab, you don't have to go to the lab. Okay, yeah. I think for most of our labs, you can do it wherever you want, right? The reason to go to the lab is to ask questions. I think if you cannot do it, have difficulty in debugging, then the TA will help you. Or sometimes I will go there as well. Okay. All right. So this is our agenda, and before this, I'll just introduce you maybe some constant, right? The most basic constant. So the first one is the speed of light. So we're going to use it all the time. So we denote that as c. So what is the speed of light? Everyone knows? Yes?
3 times 10 to the 8 meters per second.
Very good. Very nice. So we need to somehow remember that. And then we need some SI prefixes. So basically, we know K is 10 to the power of 3, right? And mega, so kilo is 10 to the power of 3, and mega is 10 to the power of 6, and the G is 10 to the power of 9, and last one is T, tera. So tera is 10 to the power of what? Who knows? It's 3, 6, 9, right? So it's 12. Okay, very good. So yeah, so basically we're going to use that all the time, right? Because in the wireless communication, so when we talk about the usable frequency, we'll talk from maybe like 100 hertz until terahertz, right? But not in this class, but normally, now, so basically we're increasing our transmission frequency a lot, right? The reason is that once we go up to the higher frequency, we have a much wider bandwidth, right? For example, in maybe around like 300 gigahertz, so we may have like 1 gigahertz like as our bandwidth, right? So we have huge bandwidth. So then we want to go to higher and higher bandwidth for wireless communication. Okay, so those are the basic concepts. And now let's see the first one. So yeah, so I will not repeat it. It's just a wavelength of a signal. Let's see what is a wavelength of signal, okay? For wireless communication, usually what we really transmit over the air is some kind of sine and cosine wave. Okay, so that is what we really transmit, right? For example, the signal that is transmitted can look like this, right? If it's a cosine, yeah, it will be look like this, right? So here is 0, and here and this is what we transmit. Okay, and you can think this is like time or distance. Okay, and now let's see what is a wavelength basically. Oh, in my notes I use a sine wave, but it doesn't matter. So, oh, by the way, so I will upload my notes to the website and Canvas as well, right? So I think it is suggested you still take some notes, right? Because that can help you to follow, right? But you don't have to. Okay, I will upload all my notes. So there will be more content on my notes, right? Because I don't think I want to write everything here, right? There will be more clear, detailed explanation on my notes compared to the board. All right, now let's see what is a wavelength, right? So basically, a wavelength is the length of one period, right? So normally, if we look at the cosine sine signal, that will be a periodic signal, right? And the wavelength is defined like this. So this is the wavelength. Basically, it's one period, right? So this is our wavelength. Length. Okay, so basically the wavelength of this the electromagnetic wave is just the distance spanned by one period of this signal. Okay, so that's basically the concept of wavelengths. And now let's see how this will propagation, right? So basically we see at some distance, we denote this as a d, right? So basically, let's see what would be the signal look like when we want to receive the signal at some distance d. Okay, so basically in this case, so let's say here what maybe you can consider here the signal start from here. So that is like a distance 0, right? If the distance signal like that, we denote that as maybe 0. So here is the distance 0. Okay. If the signal here look like this, let's say A cosine, let's say omega t. So omega is a frequency, right? So if you have learned signal system, for example, you should be pretty familiar with this notation, right? So by the way, what is the unit of omega, if I write it in this way? Radius. Exactly. Yes. Radius per second. Very good. Radius, not per second. Yeah, radius per second. Okay, great. Right. And now let's see if at some distance d, so what does the signal look like, right? S of d. So that will be A times cosine omega of, so because now we need some time to transmit the signal from 0 to a distance of d, right? So basically, what we received here is a delayed signal, right? So we denote that as omega times t minus tau of d. The delay is a function of the distance, basically. Right? Does that make sense? Okay. Any questions so far? So this is a signal we received at a distance of d. Okay. So we know the speed of the wave, right? The speed of the wave is nothing but the speed of the light. Right? Speed of the electromagnetic wave is the same as the speed of the light. Okay. So then, can you tell me, me right here. So can you tell me, so what is the relationship between d and tau? Right, d is the distance, right? And tau is how much time we need to traverse this much distance. Right, then what is the relationship between d and the delay, the tau? Should be time, yes?
D over c.
Yeah, exactly. Very good. Okay. Or I can write d equals to c times tau, right? Yeah, the next step, we can see, so from here, we can see that tau equals to d over c, right? So basically, Yeah, this is the speed, this is the time, and then we get times these two together, we get the distance, right? Yeah, we're okay, right? So this is relatively straightforward. And now, so given this, we can write our signal as Td as A multiply cosine omega t minus tau, so where tau is d divided by c. So we can put omega inside, and then we have d over c. Okay, so far so good. Yeah, the reason we're doing this is that we want to see, so how can we compute the wavelength, right? Because the topic here is the wavelength, right? And the wavelength is basically the length of one period of sine or cosine signal, okay? So can you tell me what is the wavelength? The wavelength is basically a distance, d, but it's just one period, okay? So what is the, can you tell me what's the wavelength? Or how can we compute the wavelength? Yes?
You could look at how much delay of the signal, so like the shift of it, happened over that distance that you know, and then you calculate it by just delay.
Very good. In particular, yeah, I like what you said. Definitely is correct. So we need to look at this delay, right? So then we need to let the delay omega d over c equals to what to get the distance? So it's a one period, right? So delay has to be, so what is the period of this signal? Oh, yeah, let's say this signal, right? 2 pi, right? Very good. So we just let omega d divided by c equals to 2 pi. Okay, and then from here, we can get the wavelength d equals to 2 pi c over d. Oh, sorry. Omega. Okay, and we can use another notation here. So normally we use lambda to denote the wavelength, okay? But I don't want to do this now. The reason I'm not doing this now is that, so can you tell me the unit of this? Yeah, let's see, right? So 2 pi, there's no unit. So for the speed of light, is meter per second, right? And for omega, so what is the unit? It's rad per second, right? Then what we get here is meter per rad. Right, does that make sense? Yeah, or is that weird somehow? Kind of, right? So why the wavelength is this kind of thing, right? So normally that is not what we do, okay? So what we normally do is that we use for the frequency, we don't use rad, we use the concept of hertz, okay? So we know that omega equals to 2 pi f, where f is hertz, right? So basically now let's use this notation, plug this into this. Let's see what we get. So basically, now we just use, let's do it from here. So basically, omega equals 2 pi f, and we replace d as lambda. So that's our wavelength. Divided by c equals to 2 pi. Okay, and then we can cancel 2 pi. Now lambda basically equals to c over f, right? Okay, and then now let's see. Now let's check the unit, right? See whether it makes sense or not. So the unit of f is what? Is hertz. Okay, so what is hertz? Yeah, it's 1 over a second. 1 over a second. Okay, so now let's check it. So basically for c is meter per second, and for frequency is 1 over a second, right? And second canceled, so that is meter. Okay, that sort of makes sense, right? Because it's a wavelength, right? So it should be a length measured now. A wavelength, we can, if you compute in this way, so we have the unit of meter, so which cannot make sense. Okay? So far, so good? Yeah, so this formula is extremely important. So this formula characterizes the relationship between the wavelength and the frequency. Okay, wavelength and the frequency. So basically, it tells you that if we increase the frequency, the wavelength will become smaller. Okay, which kind of makes sense, right? If we increase, if we increase the frequency until extremely high, like infrared or even optical, then it doesn't look like a wave anymore, right? Because the wavelength is too small. Okay, great. So now let's see some examples. Let's see how we can compute the wavelengths. So usually for cellular communication, okay, like our cell phone. So who knows what kind of frequency do we use for cellular so far in the US? Yes?
Like 4 gigahertz, 5 gigahertz?
Say again?
4 gigahertz and 5 gigahertz? Or?
Not really. Yes, much higher than that. I mean, for the current, like 4G, 5G. Yeah, it's okay. I mean, it's just a number. You want to say something?
There's 6 gigahertz band, and then there's the old GSM stuff, 1.9, I think.
1.9 what?
Gigahertz. That's old GSM, never mind.
Yeah, I think, actually I'm confused a little bit. For Wi-Fi, I think we have 2 bands, right, which is 2.4 and 5 and 6, 3 bands actually. But for this, we have this band before, but now, maybe I think we have more band here. But anyway, so at least, normally for cellular, so the band that we're using, or the carrier frequency that we're using, is 900 megahertz. Okay, so it's a very good frequency. We can transmit, over a relatively long distance using this kind of frequency. And let's say, given this frequency, so what is the wavelength that we're using? Okay, so we're going to use the formula to compute it. So basically, it's C over F, right? And we know C is 3 times 10 to the power of 8. And F is 900 megahertz, right? So 900 megahertz is 900 times 10 to the power, remember mega, and there is what? 10 to the power of 6, right? So it's 900 times 10 to the power of 6 is 9 times 10 to the power of 8. So we'll have 9 times 10 to the power of 8. So we have 1 over 3 meters, right? That's basically the wavelength, okay? You can see it's pretty big, right? So why this is important? It's because conventionally, now many things are not valid anymore. But normally, so when we put antennas on the transmitter, so we need to separate the antenna by at least, I forgot. It's at least, or I think at least half of the wavelength, right? So basically, the wavelength will tell you how can you design the distance between antenna. Okay, that's why this number is very, very important. That makes sense so far? Okay, so on the other hand, so if we look at AM radio, okay, so if for AM radio, so the frequency is around 1,000 kilohertz. Okay, so that is 10 times 10 to the power of, kilo is 3, right? So that is 10 to the power of, that is just 10 to the power of 6, right? Okay, in this case, if we compute the wavelengths, so lambda equals C over F, so that is 10 to the power of 6 divided by, that is 3 times 10 to the power of 8 divided by 10 to the power of 6. And then, so that is 3 times 10 to the power of 2, so that's 300 meters. Okay, that's a pretty long distance. Okay. Yeah, that's the wavelength. Okay, any questions? Okay, great. Yeah, let's continue. Yeah, now let's see our second topic, so which is the effect of the surfaces of propagation. So basically, so the RF will propagate like this, right? If here is a source, right, it could be anything, and then when RF transmit from the source, it will look like this. Okay, so it will transmit to all the directions if it doesn't touch anything. Okay, like in the free space. So this, it's like omnidirectional. Okay, so now the problem is that when it touches something, what will happen? Okay, so basically when the RF signal interact with the surface, in the environment, so basically what will happen will depend on two things. So one thing is the wavelength, okay, and the other thing is the size of the object, okay, or the features of the object, okay. So now let's see, we have three cases here to consider. So the first case is reflection. Okay, so basically the reflection. So basically reflection is like, if the wave touches something and then it will reflect, right? So when this will happen? So this will happen when the surface is relatively smooth. Okay, in other words, when the feature of the surface is much bigger than the wavelength. Okay, so that will happen. So basically, reflection means that if I have a transmitter here and you have a receiver here, then we're definitely going to have a direct path, right? Because the transmission is like this, omnidirectional. And then if here is a ground with relatively smooth surface, so we are gonna have a wave look like this. Okay, so this is a reflection. Okay, so this happens when the feature of the surfaces is larger compared to the wavelength, right? So let's write it down. The features of the surface are larger compared to the wavelengths. Okay, so that's reflection. And the other thing that we can have is called diffraction. Okay, so basically, the diffraction can occur when the electromagnetic wave impinges on some sharp object. Okay, so basically, if we have a signal here and if we have a receiver here, then so the object is like this, it's very sharp. Then when the wave can kind of pass through it, right? So that's diffraction. Okay, so this will if it's kind of like a sharp object. Okay, so it needs to be sharp. Okay, the last one is scattering. Okay, so scattering is in the opposite of reflection. Right? Let's say if the ground is like not smooth, right? There's a lot of things going on here. Okay, so basically the wave will be reflected to everywhere, right? So that's basically scattering, right? So it looks like this. Let's say if we have something like this, right, which is not smooth, then here is our input. I mean, if the wave will hit the ground like this, then the output will be like, the reflection will be like everywhere, right? So that's basically scattering. But the important thing here is that the features of the surfaces are smaller compared to the wavelengths. Okay? Is that clear? Yeah, so that's basically what will happen when the EM wave will hit a surface. Okay. Okay, and given that, now let's see. So if we use antenna for transmission, what will happen? Number 3. It's very nice to have this big board. I don't need to rewrite everything. Number 3 is antenna and propagation. Okay, so basically when we have antenna, so it is the same like before. So let's say here's our antenna. Then the wave will be transmitted like this, like what we drew before. I should now erase it. Okay, so this is the most ideal and theoretical transmission pattern. It's called omnidirectional, or it is called isotropic. Okay, so when we use the antenna, so we have 2 questions that we want to answer. Okay, so basically when we transmit something, right? So the important thing here is that we want to measure the received power, right? So we transmit using a power, then how much power that we can receive. Okay, so here we want to understand 2 things. So one thing is that, so what is the exact relationship between the received power and the distance? Okay, and the other question that we want to want to solve is that what is the relationship between the received power and the transmitted frequency? Okay, so those 2 questions are what we want to answer. So let's write it down. So that's the important questions. The number 1 is, how does the received power vary with distance d? And the second question that I want to answer is that, how does the received power vary with frequency? F. Okay, and you can see that frequency might be a function of the wavelength, right? Okay, so our goal is to answer these 2 questions. Okay, so let's see how we can do that. Right, so basically, as we said before, so what we're considering here is like this, right? So this is our transmission pattern. So that's like 3D, right? So it's kind of the wave will propagate like sphere, right? Because it's going to everywhere, right? So for this specific transmission pattern, we have a name for that. It's called isotropic radiator. Okay, yeah, that's a theoretical concept, right? In reality, it may not be exactly like that, but so this is our starting point. So it's an isotropic radiator, and sometimes we call that isoradiator. Or isotope. Okay, so they're all the same. So isotope antenna. Okay, great. So given this, so can you think about how can we know the received power, right? Because if we want to propagate like a sphere, right, and when we receive it, right, we only receive like part of it, right? We cannot receive from everywhere, right? So what should be the received power look like? Yes?
Like the area of that sphere, which is that piece of the area of the entire sphere that it receives?
Yeah, we cannot receive the entire area, right?
Yeah.
But the idea is definitely correct. We can only receive part of the area, right? Because, for example, let's say if we have, here is our transmitted antenna, and here is our receive antenna, right? So the wave will propagate like this, right? And then up to here, we can only receive this much, right? Everything else is gone, right? So that's basically the idea. Therefore, it basically means that, so we want to see what is the density of the power that can traverse within this distance, right? So we want to compute the power density that, at this point, basically. Okay, it depends on the size of the antenna. If the size of the antenna is big, then we can get more power. If it is small, we can get less power, right? So, but the important thing is that what is the power density at the receiving point? Does that make sense? Right, so can you tell me how can we compute the power density? So we need to know what is the area of the sphere, right? So let's say the distance here is d. So what is the area of the sphere? It's the area, we need to compute the area of a sphere with basically radius of d, right? So what's the area? Yes?
Pi d squared.
Say again?
Is it pi d squared?
Almost. Yeah, we have a 4 in front. Yeah, it doesn't matter, right? So, okay, great. So this is basically the area. Yes?
Should that not be with R as opposed to the surface area?
Yeah.
Pi r squared?
Yeah, R is the radius, right? So now since this is our center point and then our receiver is here, so the distance is d. So that's basically a radius, right?
Sorry,
So yeah, that's R. Yeah, very good. Okay, excellent. So now let's say if the transmit power is PT, right? Normally use PT to denote transmit power and PR to denote the receive power, right? So if the transmit power is PD, then we know the power density at the receiver or at a distance of d. So that will be equals to what? PT over 4 pi dr, right? So the power divided by the area, so that will be the power density per unit area. Okay? That makes sense? Okay, so we can only use this kind of thing, when the distance is far enough, right? If the distance is too near, something doesn't work. Okay, depends on physics. Okay, so but that's not focused on our work. So we say, okay, so let's say the distance is far enough. So normally, if we don't work on almost like terahertz domain, we're fine. Okay, it's so-called far field. Okay, so for almost all the communication technology or the wireless communication technology we're having today, so we only need to look at the far field. The far field power density. Okay, so basically it means that we can use this formula. Okay, so basically, when we So first of all, so this is the far field formula. If it's near field, it's not like that. Okay, and the other thing is that so normally for the transmitter, we have another factor called the transmit gain. Okay, so basically, instead of this formula, so the far field power density, so we can write that as a PT times GT divided by 4 pi d squared, where GT is the transmit power gain. Okay. Yes?
Well, wouldn't the transmit power gain be 1 because we're talking about isotropic antennas?
No. Yeah, I don't know how the physics work, but I need to double check it. I cannot answer. Yeah. But I don't think so. Yeah.
Will the transmit power gain be like greater or less than 1 total?
Greater. Yeah, because it's a gain, right? If it's less than 1, then we don't need to do anything. Then we can achieve it, right? Yeah, normally when you use antenna, then we would have this factor there. Okay, great. Yeah, let me finish one last thing here. Yeah, so if we have antenna, we have a transmit antenna gain. So you may ask whether we're going to have any receive antenna gain, right? Turns out, yes, we do. So we have a receive antenna gain as well. If we design the antenna correctly, we have a receive antenna gain. We call that GR. Okay, so basically how it works is as follows. So the received power, PR of D, so this is the received power at a distance D, right? So this should be this formula, right? Because we just compute it, right? This is power density, okay? So basically, yeah, let's say the receive antenna, we just capture, the unit power, right? The power over unit area, okay? So it should look like this, right? So it should be PT times GT divided by 4 pi d squared, right? That is what it look like. However, so we have this effect here, right? So basically, this will determine a concept called receive aperture, right? So we denote that as AE. So AE is called if the effective aperture. Okay, so the relationship between the aperture and the received gain is like this. So AE equals to lambda squared GR divided by 4 pi. Okay, so it's like, it's like an aperture, right? We capture, the received energy. Okay, and given this, we can use this formula and plug that in here. So that's PT times GT, and use that. So that's lambda squared GR divided by 4 pi, and we'll have another 4 pi here, and we'll have a d squared, so that's basically 4 pi d, entire thing squared. Okay? Right? Actually, this equation is pretty important, so that's called free space equation. Okay? So from here, we can answer the first question, right? So the received power basically equals to this, right? So then what is the relation between the received power, PRD, and the distance? Very good. So it's proportional to 1 over d squared, right? Okay, so now let's see the second question. So what is the relationship between the received power and the frequency? So can you figure out? You remember important formula that we introduced in the beginning of our class, right? So what is lambda? C over F. Very good, right? Therefore, lambda squared is basically, let's write it here. So that's equals to PT GT. Lambda squared is C squared over F squared, and then times GR divided by 4 pi D squared. And then we can say this PT GT C squared GR divided by 4 pi D F entire thing squared. Okay, and here is our frequency. Therefore, so we can see the received power is proportional to, not equal. Proportional to 1 over F squared, right? So this basically means that if the distance is longer, then we receive less power, and the relation is squared relation, which makes sense, right? But what is non-trivial probably is like this, right? So when the frequency is higher, then the received power is much less, right? So then it basically means that, as I said in the beginning of the class, so when we move to a higher frequency, we have a much bigger bandwidth, right? Bandwidth basically means resource. We have much more resource to transmit, right? For example, in the 900 megahertz, our bandwidth is like 20 megahertz. But you have like 800 gigahertz, then our bandwidth is like maybe not 800 gigahertz, maybe like 30 gigahertz. Our bandwidth is like 1 gigahertz, right, which is way bigger than the 20 megahertz, right? But the downside here, one of the downside here is that, so our receive power will be much less because the frequency is much higher. Okay, so we need to be careful. Okay, so yeah, we finished point 3 here. So, and then I'm going to cover this in the next lecture. So, which will be a video that I'll upload. Okay. Thank you, everyone. So see you next Wednesday, right?